Calculus 2, 6.2 volumes by cylindrical shells. In 6.1, we introduced the disk method. This was slicing up a solid. It usually produced a circular disk. It had some thickness, though. That thickness we'd call dx or dy. And it also had a radius, we called that little r. The area of that was pi r squared. And if you wanted a volume, you'd multiply by this thickness, dx. And so the disk method gave us, it really had in general, from A to B, some area of the base. It doesn't have to be a circle, but that's what we used an awful lot, times the height, dx. So it's really just, it was like a cylinder. But this one had, I guess we're doing slicing to get that disk. Now, we also then had the washer method. Now the washer method was similar to the disk method, except with that thickness, which could be dx or dy depending. We also had a hole in the middle. That's what made it a washer. So we had a little radius and a big radius. And these were circles. That was the integral from A to B of pi. So this was the big R squared minus the little r squared because, oh, and these could be functions, so this would be r of x dx. So it's the big R minus the little r that gave us the area of that washer, and then times the thickness. So, and this one, once again, because we used circles an awful lot, it shows up an awful lot. This is pi r squared dx. But that's not the only way to do those. If you got any slice, if you could figure out the area, times that height, dx. But circles were used a lot, and certainly washers is using circles. In this section, we introduce the shell method. Now, you'll notice the title up here is Volumes by Cylindrical Shells. So it's going to use the same sort of idea. We're going to use a cylinder. The cylinder does have some thickness, but that thickness is for the dx or the dy. But now we've got this shell that we start building these. So there's another shell perhaps here that gets sort of built. If you've watched any of these 3D printers, it sort of uses that idea, because it'll build another shell here, cylindrical shell, and it keeps filling these in until it gets to, this is another cylindrical shell. It fills that in. It's hard to draw a little bit, but it's sort of easy to understand, because the shell method, we take and cut this one of these. It's just like these. I guess we had 4 steps here, right? One was draw a representative disk or washer or shell. Step 2 was to figure out the function that this would entail. And step 3, the limits, A and B. Step 4 was calculate the integral. We're going to do that here also, same idea. You draw a representative shell. You figure out this surface. Now the dx is the thickness, but if you slice this down the edge and roll it out, you really don't get a cylinder anymore. You get a rectangular solid, although it may be very, very thin. This is the dx, or the dy. That's this little thickness. We just need to know the length and the width, or the height and the width, or whatever you want to call it, the L and the W. Now, if we've cut this from a circle, then the L is going to be the circumference of that circle. And if you remember, if this is R, the circumference is 2 pi r. And if we can find this height, say, let's call it h, the surface area is 2 pi r h, and then we have to multiply by the thickness, the dx, and take it from A to B. So A to B, 2 pi r h dx. Now these two functions, this would be a function r of x perhaps. This could be another function h of x, something in terms of x, since this is with respect to x. So you might say, well, when would you use this? There are times when the washer method becomes very clumsy and maybe even a little hard to follow. And this shell method does make it easier, especially for the calculations. But the problem with the shell method, it's usually harder to set up. You've got to be able to draw a bunch of pictures. So, when some of these slicing methods are awkward to apply, we use that. One reason for that could be we need this in terms of x. If you're using dx, and you were given, say, y equals 3x minus x squared, then it would be better to do this in terms of x instead of terms of y, right? But if we were using dy, then we'd have to solve for x and find that. And many times for that washer method, you can't just change that thickness. It doesn't work the way it's drawn. Try to solve for x here. What do? Well, you've got an x squared and an x. You could do it if you want to use the the quadratic formula, where you say that a is a -1 and b is 3 and c is 0. Then it would be the opposite of b plus or minus the square root of b squared, which would be 9, minus 4ac, but c is 0. So it's just that all over 2a, which is a -2. And this is okay. I'm sorry. These are x's, though, right? That's what y would equal. That's what x would equal. And we'd have to, all of a sudden, it becomes a little awkward and crazy to do. So, let's look at a specific example. How about if we use this 3x minus x squared, and we'll have a picture something like this. And we take this region and spin it around the y-axis. And so you get this it's sort of like a washer, so it's tempting to use a washer, but it's a little bit different. You slice it this way, and perhaps this one would work, but if this is the function y equals 3x minus x squared, in order to use your slice here as the representative, you'd have to solve for x, because you'd want to use dy, and you could come up with that. It would be x equals, and I could go through this again, but 3/2, you could use plus because we could use this the right side, the square root of 9/4 minus y. And the problem is we'd have to find the antiderivative of this. That's what makes it awkward. Sort of a scary problem. So, how do we use shells? Well, let's try this again. Let me be a little more careful with this drawing, but these are not very easy to draw. So this is the picture, and hopefully you can envision that. It's sort of like a donut cut in half, sort of. So we're not going to use a slice of it. We're going to use cylindrical shells. we're going to say, okay, let me take a shell out of this thing. And then I'm going to make it come over here and have this shell. So now I've got this shell, a representative shell. This is dx. Aha! We had to use y before. Now we can use dx. So if this is the function, let's see. Let me look at this again. 3x minus x squared. And the y equals 0, of course, for the x-axis. And we're doing this about the y-axis. So now we can say this radius, which is just x, and I'm giving these numbers, but it may or may not just go up to 3 here or something. Maybe it goes up to 1. I just want to give it some numbers just to show you. We're going to go from 0 to 3. The 2 pi r is the x. H is the height of that function. 3x minus x squared dx. And that is an easy function to find the antiderivative. And that's the whole reason for shells. It's a little harder to set up, but it's a lot easier to find the antiderivative. So, once again, we would like the integral from a to b 2 pi r h dx or dy or whatever variable. So we need to find a and b, the function for r, the function for h, in terms of whatever variable dx dy. This is the shell radius. And this is the shell height. Now if we do this horizontally, it's really the shell height would be laying down. Let's use our friend y equals the square root of x. And our other friend, I guess, y equals 0, the x-axis. But let's wrap this around the y-axis. This may be a little easier to follow. So, you can do the square root of x. Oh, and we want to take this up to 1, we'll say. So then we know this height is 1 here. We're going to swing that around. So over here we have also that mirror image. And we have this solid. Take a representative shell. Now this shell, I've got it going all the way to the outside, but it need not, you're filling in this inner part too. You're building up all these little shells here. There'd be a shell in here that you could use as a representative. Does that make sense? But all you need to remember is, and maybe that one inside is a little nicer to use, the integral. Now, because we're doing this with respect to x, because that's this thickness, we're going from 0 to 1. And I may be asking these questions on quizzes. So the function, I might ask the method too. You'd say this is shells. The function is that square root of x. We want the radius, I guess, which would just be x. And this function, the height, would be square root of x. We want the limits of integration, a and b, 0 and 1. And we want to set up this integral. So the integral from 0 to 1, of 2 pi r is just x. H is the square root of x dx. And all of a sudden this becomes sort of a simple problem. If you use fractional exponents, this is 0 to 1. The 2 pi can even be pulled out front. This is really x to the 1 plus 1/2, or 3/2 power dx. And the antiderivative of that is add 1 divided by the new exponent. So you add 1, which is really 2/2, so this is x to the 5/2. When you divide by 5/2, you really multiply by 2/5. And this is from 0 to 1. Plug in a 1, sort of nice, that's why I chose it. You get 2 pi, and 1 to the 5/2 is 1 times 2/5. And of course, when you plug in a 0, you subtract 0 from that. So this is really 4 pi over 5. Does that make sense? Okay, let's do an example step by step. This is CalcII, page 328 in your text, number 6. It's a region defined by y equals 9x over the square root of x cubed plus 9, and the x-axis y equals 0, from 0 to 3 about the y-axis. How does that even look like? Let's bring our friend in. Guess I need to see what that is. And let's put it in our calculator. Clear. We've got 9x, so we don't need any parentheses around that. But now we need some, well, we got the square root that'll help us here. The square root of x cubed plus 9, close. And we want for this from 0 to 3, so probably we want this from a -3 to 3. So I'm going to make my window a -3 to 3. And then I'm going to do a zoom fit. Your calculator takes those x-coordinates and finds out the highest y-coordinate, and that's the top of your window. Oh. It also finds the lowest one. But we're going from 0 to 3, so we don't need anything lower than that. I'm going to change my window y-min to 0. And now when you graph it, you get something like this. Now it looks like the square root, and I guess it makes sense. There's a square root in it, but it's not exactly the same. But remember, this height is going to be the square root. We're going to wrap this around the y, or rotate it around the y-axis. So there'll be another copy of that over here. And we're going to get sort of like the thing we had before. So why should we use the shell method? Well, because of that crazy function over here. So let's first of all draw it. It's going to look sort of like before. So this thing right here goes up to 3. And there's one over here, goes to -3. Our representative shell, it's probably better to pick something out of the middle. And that thickness is dx, and it'll be sweeping around here. We need this radius, which is just x, and the height is whatever x we plug in will be that function. So, once again, first of all, what method? This is going to be shells. We're going to do this, the radius of the shell is going to be x. The height of the shell is going to be that 9x over the square root of x cubed plus 9. That's the height. That's this thing right here. And the limits of integration, x goes from 0 to 3. That's what this x is. 0 for that radius up to 3. And that's our integral. So it's 2 pi r is x. H is this crazy 9x over the square root of x cubed plus 9 dx. And you've got to know that they gave you something that was not horrible to integrate. This thing, when you see that, remember what to do. If you see something in the denominator, first of all, this becomes 9x squared. I'm going to pull out the 2 pi. Integral from 0 to 3. The x I'm going to multiply, and it's 9x squared. And I'm going to put the dx up there with it because they're going to go together. This square root of x cubed plus 9. Now, many times you pick what's inside. If you can, you pick the whole square root. But in this case, let me change colors. These are Christmas colors, I guess. Huh? U is going to equal the x cubed plus 9. The derivative of u is 3x squared dx. Well, we don't have the 3, we've got a 9x squared, so we're going to multiply both sides by 3. So now we've got what to replace this with up here. And this is just u, the square root. So now we have this new integral. The 2 pi doesn't change, that's constant. We've got the du in the numerator and the square root in the denominator, but I'm going to write that as u to the negative 1/2 du. But you got to use these limits of integration. So back over here with u, plug in a 0 and you get 9 for u. So it's going to start at 9 and go up to plug in a 3 and you get 27 plus 9, which is 36. Now it's a little easier problem. 2 pi, add 1, so it's u to the positive 1/2. Divide by 1/2 is when you multiply by 2, from 9 to 36. So this is, let's see, it's really 4 pi, u to the 1/2. Plug in a 36, square root of that is 6 times 4. 6 times 4 is 24 pi, minus, plug in a 9, square root of 9 is 3, 3 times 6 is 18, 24 minus 18, now I'm getting confused, did I do it? Oh, no, I did that right. Okay, sorry. This should be right. 24 minus 18. I'll check it and see. So it's 6 pi. Just check it and make sure. It doesn't feel right. Something's wrong. Well, yes, because I said it and then didn't do it. No, that's okay. That's good. That's correct. I think we're already here then. 6 pi. Let's see. Well, I'm glad I made this mistake. You can go too fast. Remember, this is a 3 du, not just du. So I needed another 3 here, which would make this 6 instead of 4, which would then take 6 times 6, which is 36 pi instead of 24 pi, and 9 is 3 times 6, which is 3 times 6. Maybe I did that completely right there. 36 minus 18. But that 6 should have been up here. If I can keep this on the screen. Sorry. 6 should have been up here times 2. This really is a 12. So now that makes more sense. 6 times 12. So what is 6 times 12? It's 1612 or 72 pi. This is 3 times 12 minus 36 pi, and that's what I was looking for, 36 pi. Whew. Don't go too fast. You'll make simple mistakes. So it seems like I need a little more practice too. So Calculus 2, number 22. We want these three functions, y equals the square root of x, y equals 0, and y equals 2 minus x. Use the shell method to find that volume when you generate that volume about the x-axis. If you have trouble drawing these, your calculator can help, but you got to draw them eventually. So if you put in the square root of x and 2 minus x, and y equals 0 is just the x-axis, you can do a zoom standard, and it gives you probably a window that has it in it. But you don't want everything. You want this little area down in here. So I am going to zoom in. Number 2. Now it zooms in pretty good there. Let's zoom in again. Notice it's blinking. Press enter. So that's even better. This area here is what we'd like. So if I can draw that and then mimic it below, right? Because it's about the x-axis. So let me see if I can do that. So let's put it over here. Mine, as soon as you touch that, it's going to disappear. So you've got the square root, and then you've got the 2 minus x. And here's the square root and the 2 minus x. Now, you can use others, but I want to use the shells so we can practice, because I'm a little rusty. So here, now we're using, the horizontally, we're picking our shells. And so we're doing this dy with respect to y. So all of these things need to be solved for x. So we need x equals y squared. And this will be okay because this is positive. We got everything. That'll be good. Here, we don't have to worry about y equals 0. But this one is x equals 2 minus y. Sort of add x, subtract y. Now, we need use shells. I guess that's our first step. The second step, we need the radius, which is this height here. Now that height is going to change as you move. How do you want to say this? It'll go from, it'll be the y value, and it'll go from 0 to 1. So it's this y value going from 0 to 1. That's where this point is here. The square root. This is when y is 0, x is 2. So this is 2 here. This is 1 here. And at 1, y is 1. And so we know what these points are. So the radius is just y. The height is this horizontal. But now we've got two functions to deal with. So it's this, it's to the left of the line and to the right of the curve. So how do you write that down? Well, since we want, if we think of the line as 2 minus y instead of in terms of x, and the curve is y squared, it's really the 2 minus y, that one, minus the y squared. That's what gives us this height. So the height is 2 minus y minus y squared. So we got the height. Oh, we need the, what does it go from? Y goes from 0 to 1. So the integral from 0 to 1 of 2 pi r, which is y, h, which is 2 minus y squared, dy. That's the thickness. And then you find the antiderivative. Pull out the 2y, or 2 pi rather. 0 to 1, let's distribute this. 2y minus y squared minus y cubed dy. So this is the 2 pi. Now what's the antiderivative of 2y? Well, you add 1 to the exponent. So it's 2y squared divided by the new exponent. Minus, add 1 to the exponent, y cubed over 3. Minus, add 1 to the exponent, y to the 4th over 4. Evaluated from 0 to 1. Plug in a 1, you get 2 pi. This is just a 1 here, times 1. Minus, this is a 1/3, minus 1/4. And because all of these have y's, when you plug in the 0, that just becomes 0. So what is 1 minus 1/3 minus 1/4? Well, I'm going to run out of room. You get 5/6. I'm sorry, 5/12 times 2 is 5/6. Anyway, 5/6 pi or 5 pi over 6. You can do that work a little bit if you want. Maybe I'll show you on the calculator how that can arise. Let's show how this calculator can be helpful if you need some to make up some time. If you do 1 minus 1/3 minus 1/4, it gives you a decimal. If you go math frac, changes it to a fraction, 5/12 times the 2. So it's 5/6. We should do one more. Okay, calc to another example, number 32. The region bounded by y equals 2x minus x squared and y equals x. I think I messed this up. This page should be about the y-axis, and this about the line x equals 1. About the y-axis, you should be able to do that one. We're going to have this a little different about the line x equals 1. So, graphing this is important. Your 2x minus x squared is a parabola that opens down. Here's the point 2 and 0. Y equals x is the line here. Now the region that's bounded is only this part on the left. But notice that this is the line x equals 1. And so that gives us really the other part of this shape, because we're spinning it around here. Here's my representative. It's going to be a thickness going down here, and thickness going down here. So all of these cylindrical shells, we need the rate of, let's go the steps. Number 1, this is shells. The radius, because the thickness is dx, let's do this with respect to x. So the radius is really just this x over here. But it all depends, because there's going to be some of these larger and smaller ones depending upon where it is. So this radius is going to go from 0 to 1 as this spins around here. And so we're going to use this portion on the left. So maybe sometimes it's good to look at those maybe first. A equals 0, B equals 1. That means the radius is going to be this x value. When you put in an x, you're going to measure to this center, which is that x equals 1 line. Now, you can write that as 1 minus x, because you're going to have this as the radius inside. Does that make sense? So you're going to start at 1 and subtract wherever that x is to get this radius in here. So the radius is 1 minus x. The height is this height, which is always going to be as high as, I guess, how do you say that? It's really just this little one in here that we're looking at when we start stacking these up. So it's the parabola minus the line. The parabola, which is 2x minus x squared, minus x. And then this goes from 0 to 1. So my drawing was maybe not so great. I went down too far. I should have only gone down to this spot right here, not all the way down here. So the integral from 0 to 1, 2 pi r is just going to be what, 1 minus x. And the height is 2x minus x squared minus x dx. So let's collect a little bit of this. 0 to 1, put the 2 pi outside. This really becomes 2x minus x is just x minus x squared. And when we multiply this out, we get x. We get x cubed. We get a negative x squared and a negative x squared. So I guess let's write all this out. 1 times x is x. 1 times negative x squared. Negative x times x is a negative x squared. And a negative x times a negative x squared is a positive x cubed dx. It's a cube. So 2 pi, 0 to 1. Let's put this in order. X cubed minus 2x squareds plus x dx. I'm going to run out of room again. Add 1 to the exponent, x to the 4th over 4, minus, add 1 to the exponent, 2x cubed over 3, plus, add 1 to the exponent, x squared over 2, evaluated from 0 to 1. So you get 2 pi, and this is 1/4 minus 2/3. Let me put it up here. Plus 1/2 times the 2 pi. So this is 1/2, and that's 3/4 minus 2/3. Common denominator is 12. This is 9/12 minus 8/12. So this is 1/12. But times 2 pi means it's really just pi over 6. Does this make sense? These can take some practice. If the assignment isn't enough problems to practice, do the odds. Make sure you get the answer that you can look at in the back. That's section 6.2. Sort of fun.